Welcome back to the Structured Cabling lecture series. In this lesson, I will cover cable performance fundamentals. If you haven't seen my previous lectures, I will leave a link in the description for the playlist. Please recall from my previous lectures that copper cables are popular because they are cheaper than fiber optic cables. They are cheaper to manufacture, cheaper to install, and cheaper to maintain. So therefore, the copper cables are a widely used cables even in 2022. The choice of copper cables also includes the use of solid or stranded copper wires, and it is a matter of where we're going to install it. Recall from our previous lecture, I said the solid core copper cables are typically used in infrastructure settings where the cable is going in the ceiling tiles, for example, or behind the walls, as opposed to stranded cables are more flexible and used for patch cables, etc., etc. We also mentioned that the fiber optic cables are used for infrastructure cabling as it can provide low interference and higher bandwidth over a long distances. For example, when you want to connect a nation to another nation or a wider network, for example, Japan to the rest of the world or Canada to the entire Europe with the submarine cables, we typically tend to use fiber optic cables. However, as of 2022, we use fiber optic cables even in home settings or in building settings because the cost of using it has slightly have gone down. I wouldn't say significantly, now we have some things like fiber to home, which is an internet connection that provide internet connection all the way to your home using fiber cables. Today, we will focus on technical fundamentals associated with copper and fiber optic communication cables, but the majority of this particular lesson, I will be focusing on the copper cable side of things because I will go over some fiber optics fundamentals in my next lecture. Solid copper conductors. So as I mentioned previously that we have two types, one is a solid and the other one is a stranded cables. So in copper, solid cables basically has to do with how the cable core is manufactured. And in this situation, we'll have a single strand of copper in the conductor, and it is low cost to produce. And however, these type of cables have poor flexibility and suitable for fixed installations. So what that means is basically the solid cables typically, because of it has a thick one single copper cable in there, it is not very flexible. So but because you don't need to have those stranded wires woven together to build that core, it is much cheaper to produce compared to that of the stranded cables. So for patch cables, as I mentioned, because we need that flexibility a little bit, we will be using typically the stranded copper cables as opposed to solid, but in the infrastructure mode we will be using the solid core copper cables. And there are two types of solid core cables, one called the bare copper, also known as BC, the other one called the tin copper, also known as a TC. The bare copper is just copper. It's exposed, it's least expensive, it's exposed to the environment, and therefore susceptible to oxidizing if exposed to other environmental factors. So they are basically bare copper wire covered with a plastic jacket, and when you clean it at the corners, it will be completely exposed to the environmental factors. Tin copper, as the title says, the copper conductors now have a coating typically made out of tin, but it could be lead and it could be also silver as well. Nowadays, as of 2022, I don't know which cable manufacturer actually used lead, so it's most likely going to be just tin or silver. And this protect the conductors from oxidizing when exposed to the environmental factors. it is easier to solder. So if you actually have circuit boards that we are putting wires into and you're soldering it into it, because they are probably tin or silver plated, it will typically the tin plated one especially, it will allow you to easily solder that wire onto the circuit board. However, these type of copper cables are more expensive compared to just the solid core cables with no coating at all. So the other option is called the stranded copper conductors. Stranded copper conductors are made out of, as the term stranded means, made out of multiple strands of copper thin wires that are twisted as a single conductor. So instead of have a single thick core copper cable, you will have a thin wire, so multiple thin wires that are woven together to build a one single core. So they are twisted or woven together to create a single conductor. They are flexible, so suitable for patch cables. So between the wall and your computer, for example, or wall and your server, for example, or a telephone, VoIP phones, these are the type of cable we would use. These are also used in server racks and network closet, because you need that flexibility between switches and servers and routers, etc., etc. They are more expensive, however, per feet as opposed to a solid core, and the higher strand counts mean that more flexibility in the wire, and therefore result in the higher cost associated with it. So if you buy a Cat6 cable, you could have a cheaper stranded wire Cat6 cable with a less strand count, but that means they are using a little bit thicker strands to build that core, as opposed to you could buy an expensive Cat6 cable that would have a lot more strand count, but every strand going to be now thinner and woven together to build that same diameter core as the other Cat6 cable. So the more expensive it is, the stranded, most likely they're going to have a higher strand counts, as well as a result, they're going to be more flexible. Bare copper, also known as standard bare copper, SBC, basically strand of copper only, and it is susceptible to oxidizing if exposed, just like the solid core, bare solid core wires. Stranded tin copper wires, also known as STCs, this each strand is coated with tin or lead, which can be easily used for solder onto, again, electrical components and protect conductors from oxidizing, and however this is a little bit more expensive. In IT industry, as an IT technician, you probably don't need to worry about tin wires, whether it's solid core tin wires, which are tin copper TC wires, or whether it's STC wires, standard tin copper wires, because in IT industry, as a cable installer in structured cabling, you and I typically do not install these wires onto direct circuit boards. Instead, we will be crimping on the end with a crimper with connectors, and basically using as a patch cables or infrastructure cables, right? So for you and me, it's typically we are not gonna worried about the tin side of things. But if you ever want to do electronics engineering or sometimes even network engineering, you may have to do some of those picking between this the tin wire core versus the non-tin wire core. So keep that in mind. So bare copper and the tin copper is mostly associated with people who are actually working in the cutting edge industries that may have to do with soldering onto a circuit board, for example. But for typical usage, we typically use bare copper, SBCs, the standard bare coppers, or BCs, the bare copper wires. What you should really actually care about, whether the wire is stranded or solid, not so much whether the wire is bare copper or tin copper, because we will most likely be using bare copper. So if you have never seen a stranded or a solid wire, this is the differences. So here is I just put an image that I found on the internet. So the stranded wires look like this. So it has like this stranded, you can see these individual copper wires that woven or twisted together on the standard Cat5, Cat6 cables. And on the solid core, you have this solid lump of basically coppers. So the solid one single strand of copper wire that actually does the same thing, same diameter, similar diameter as this guy, but except this one has multiple tiny diameter, smaller stranded wires that are woven together to produce the same type of wire as this. So these two wires are exactly the same kind of thing, but one happened to be stranded cables, the other one happened to be the solid cable. So this is what they look like if you actually expose those wires. Other conductor types you should be familiar with in terms of general knowledge is the copper clad type of wires, the tubular wires, also known as the waveguide wires, also known as hollow tube wires, tensile or polyester wires, braided or woven wires, and aluminum and other material made wires. Those you should be familiar with those items, but you don't need to know in depth how they are different from each other and everything. You just need to know what they are. So for give you an overview in this class without going into detail, basically copper clad wires are wires that similar to what I shown in the previous one. See, it has a copper cladding right here that would protect your wire from like wear and also in environmental issues associated with putting wires outside the plant. So in other words, if you're burying Ethernet cables outside a building, for example, in the soil, that might have copper cladding to protect the wire. Tubular wires are also known as hollow tube or waveguide wires. Those are basically wires that have basically a metal tube. So it doesn't have a core. Core is empty, but it has a metal tube in the outside. So you'll have a wire like, let's say you have a tube like this, and imagine that's a tube. And then you have a copper element mix in here. So we have all the copper right here on the outside. And the inside the wire here is hollow. So it's empty. So basically, what the tubular or the hollow waveguide wires are doing, it's using that what we call the surface effect. Basically, even a solid copper wire, basically the data actually travel outside the wire, not inside the wire, right? So I will go into depth of those in a separate lecture. Just for now, what you need to know is that, without going into technical depth details of why these are we use tubular wires. Basically, the wave will travel in here in this empty space, bumping against the tubular structure shown here. So that's why it's called the tubular wire. So you have a tube right there, and then the data will go inside here. So these are used typically in applications of microwave and other transmission wires, but so you might come across this as a cable installer, so that's why you should be aware of that. Again, I'm not going to go into technical details here, but I will maybe in the future lectures. Tensile and polyester wires, it basically gives strength to your cable, and then we have the braided or woven wires that also gives tensile strength and can be used in certain applications such as outdoor applications. And then we have aluminum and other metal related wires in specific use case scenarios where we may need to use a different metal other than copper. In the old days in Canada, for example, there were some electrical wiring done using aluminum wire. But later we found out that is not a really good metal to use for electrical wiring. So most of the newer wiring and the wiring afterwards done in Canada were done using copper wires. So you just need to know these things exist for now. But I may cover some technical details associated, especially tubular wires, in my future lectures. Reasons to use copper wire. So I mentioned that there are wires that use aluminum and other types of wires, but there is a reason why we use copper wires. Copper wires are relatively easy to produce, mass produce, because the copper, the metal, is relatively abundant on our earth. So basically, if you are doing mining for metals, copper is one of the easily found metals. So you can speak to a geologist or an engineer who are doing in the mining industry. They will tell you it's very easy to find copper compared to many other metals. So it's very relatively abundant, therefore easy to obtain and use for manufacturing wires. Copper also has a good corrosion resistance. In other words, compared to, let's say, iron, pure iron, copper doesn't rust easily, even exposed to environmental elements. Copper do rust, but it's going to be really slow compared to, let's say, pure iron. Copper is also very malleable, so that means its ability to bend and reshape without breaking the wire. So if you build a wire using a type of metal that is very low malleability factors, what's going to happen is when you bend the wire, it might break or start creating cracks really in a short period of time. We don't want that. So copper wires are very malleable, and therefore it is easy to bend and take different shapes without breaking the copper structure. And even though copper is malleable, it is relatively strong. So it has very high malleability with a little bit of a strong factor. So some metals, you will have very malleable metals. They are great for bending and reshaping. However, they are very weak. So if you pull, if you give tensile stress, for example, it'll break. But with copper, not only it's malleable, it also relatively strong, so it won't actually easily break. It's also very ductile, so it's capable of making it into a very small strength. Malleability and ductility is a little bit related to each other. So that will also help us shape the wires the way we want it to, and ductility also allow us to make small strands of wire to create those woven wires, for example. And copper is also an excellent for conductivity for electricity as well as heat. So it allows us to send data across, which are electrons, in Cat6, Cat5 cables, for example, because it has a very good conductivity. So that's why we use copper. So copper is easy to find, corrosion resistant, malleable, ductile, and however, even though they are malleable and ductile, they are very strong, and they are excellent in electrical conductivity and heat. So that's why we use copper in our wires. So there are a few performance considerations that you need to take into account when you're purchasing wires or when you're recommending wires to your clients. For copper cables such as UTP and coax cables, you need to think about impedance, which is the resistance, capacitance, and inductance. You need to think about noise, you need to think about shielding, and you need to think about grounding. So I will go into depth of what are impedance, noise, shielding, and grounding. But for now, what you need to remember is that these are factors that may and that will actually hinder the quality of transmission, bandwidth, and what you get out of your wires. This is especially important copper cables such as UTP and coaxial cables. So impedance, noise, shielding, and grounding. For fiber optic cables, you need to think about things like bend radius. So different fiber manufacturers will have sometimes the same fiber optic cable, that means same standard cable, but the bend radius may be slightly different against each other. So when you compare them, so make sure that you know those things. Broken fibers due to mishandling or manufacturing defects. This should read defects. Sorry about that. So that's another thing you need to think about. Excessive or low signal. So that's another thing. So if you install a fiber optic cable and everything is installed properly, for some reason that the fiber optic cable is not giving the performance that you're looking for, maybe you are using too much excessive LED or laser configurations, or you have too little of a laser or a LED that you're using for that particular rated fiber cable. Not all fiber cables, in other words, will use the same signaling LEDs and lasers. So you need to adjust the intensity of your laser or LED. You need to adjust the signal strength depending on the type of fiber cable you use. So if you have a performance issues with fiber cables, that's something you need to think about. Again, I will go into depth in a separate lecture, but just know these things are important. Another fiber optic cable important thing that you need to remember, which is also actually applied to copper cables too, faulty connections. So even in copper cables, if you are crimping your Cat6 cables with let's say a jack or a plug, you need to make sure that the crimp or the connections are properly done. Otherwise, that will also impact your performance of your copper cables. The same thing apply to fiber optic cables. You need to make sure you don't have faults on those connectors, including those connectors as well as the connector plugs and everything. You need to make sure that the connections are properly done. And if there is a problem, you should create that connector. So keep that. That's another place that you need to check if you have performance issue. And there are many other more factors such as environmental factors, temperature factors, etc., that will affect the performance of your cables. So I'm going to switch gear a little bit here because right now I'm going to go into a little bit of physics and math side of cabling. However, I'm not going to introduce you any math equations. I promise I'm not going to introduce you math equations that you need to remember, except maybe V equal IR. That is a basic math equation, but I'm not going to go into mathematics and physics of cable, structured cabling in this lecture series much, as opposed to the technical side of things, because most of you who are watching these lectures are technicians, not engineers. Okay, so let's look at voltage, current, and resistance as far as you and I are concerned. Okay, so the voltage, which is typically denoted by the capital letter V, can be defined as the degree of attraction between electrons and positive ions, and can be described as a pressure. So that means voltage will tell you, like if you have let's say a pipe, and if you look at the wires as a pipe, voltage will tell you how much pressure within that pipe. So the voltage is basically degree of attraction between electrons and positive ions. So that can be basically the pressure in your circuit. Current can be, which is also denoted by I, capital I, can be defined as the amount of electrons that are flowing. So if you look at a wire from one single point, and how much electrons are flowing through that point is defined as the current. So think again the wire as a pipe, and you have water flowing through, and how much water flow through that one single point is what we call the current. Resistance, which is defined by the capital R, can be defined as an opposition to the flow of electrons and resistance, and causes the voltage to drop. So in other words, whatever in that wire that causing basically resistance, or causing something, a opposite force against the voltage, is called resistance. So resistance is opposite to voltage. Higher the resistance, the voltage gonna drop. The lower the resistance, the voltage gonna increase. That's what you need to understand. And the so in this situation, we define the voltage as pressure. Then the resistance gonna be also a type of factor that impact that pressure. So that's an important thing as well. Then the next one is called the amperage, when it's comes to electricity and current. And amperage is defined with the capital A, and it is the strength of electric current and describe the amount of electric charge that is flowing. So current describe the amount of electrons that is flowing. Amperage describe the amount of electric charge that is flowing. So they are kind of related, but they are slightly different. You need to understand, this is very important. The current is defined as the amount of electron that is flowing, as opposed to amperage, which is the strength of the electric current, and that describe the amount of electric charge that is flowing. And here is something that a rule of thumb that we use: voltage is pushed and amperage is pulled. This is a very important concept. Very important concept, not in structured cabling, but also information technology and network engineering concepts, and also electronics engineering side of things. This is a very important concept you understand. Voltage is pushed, we call it is pushed, and the amperage is pulled. Why this is important? If you connect a device that is rated to a specific voltage, and the power source is higher voltage than the device will fry. Why? Because voltage is pushed to the device, and too much voltage in that device gonna burn out that device. But if you connect a device that is a higher amp rated lower amp rated to a higher amp rated power source, it's not going to burn out, because the device will only pull enough amperage to run that device. So if you connect a device to a power source with a high amperage, it's just fine. It's just going to pull just enough to run that device. But if you have a power source that is high voltage, but the device is only capable of lower voltage operations, your device will burn out. This is a very important concept when you are working in the field. Whenever you connect any cables, not necessarily an Ethernet cable, but other cables, you need to look at voltage and amperage, and remember that the voltage is pushed and amperage is pulled. So there are ways that this is actually now mitigated in certain situations where you can use any device rated for any voltage with, for example, PoE applications. So you have power over Ethernet. Let's say your power over Ethernet injector or the power over Ethernet switch or a router is rated, the switch ports on routers or switch is rated for, let's say, 25 volts or 24 volts, right? But your device is only 12 volts. What happens is the device is going to negotiate with your PoE device port saying, hey, I only need 12 volts. I don't need 24 volts. So they're going to just send the 12 volts, because if the PoE device send 24 volts, it's going to burn out the end device. So keep that in mind. So modern PoE devices actually do have capable of negotiating the voltage it needs and also the amperage they need. But again, the device will pull the amperage from the power source, but the voltage will be pushed. So it's very important that you don't plug in devices that are lower voltage rated to a higher voltage power source, unless it is that have that smart capability of negotiating the voltage. If you plug in a device that is required a higher amperage, but your power source cannot provide that type of amperage, two things could happen. In 99% of the time, your device will not power on. So if you have let's say a PoE camera plugged into a Ethernet cable, and the PoE injector is not capable of providing that power, the amperage, the camera will not turn on. But it is also possible that it could trigger a trip, like it could turn off your power source as a result, because it's trying to draw a lot of amperage and the power source just shut off. I don't know. I don't believe your power source will burn out. As in this situation, it's just gonna shut off in most cases. So keep that in mind. Voltage is pushed to the device, amperage is pulled by the device. So that is important that you check the voltage before you plugging in any devices, even network devices, because of some PoE devices may not have that auto negotiation of the voltage. Okay, keep that in mind. Ohm's law. So this is the only formula that I'm going to introduce to you. And I'm not even going to introduce you math associated with this. I just want you to know the Ohm's law exists. So the Ohm's law is a law that typically in grade 11 and grade 12 physics classes will teach you. I took grade 11 and 12 physics in high school in Canada, but sometimes even in grade 9, 10 also learn this formula too, because this is a very important formula. So the V equal IR is the Ohm's law formula, where V is the voltage, I equal the current, and the R equal resistance. Now, that means voltage can be calculated by multiplying the current and multiplying the resistance. So I, or current, is basically the flow of electrons. Electrons flow from the negative end to the positive end, as I mentioned. And R is a resistance, which is how easy for a copper or other metal wire to allow that flow of electrons. So by using this formula, we can calculate the maximum voltage in which the wire can support. So resistance, or R, we can recall from that formula is that V equal IR. So if you want to isolate that R going to be V divided by I, right? So that means resistance is directly proportional to the voltage, but indirectly proportional to the current. So the higher the current, it's indirectly affecting the R. If higher the voltage is directly affecting, higher or lower the voltage is directly affecting that. If the voltage goes up, resistance goes up. If the voltage goes down, resistance goes down. But if the current goes down, resistance goes up. If the current goes up, the resistance goes down. So that's what I mean by indirectly proportional and directly proportional. Resistance is the opposition to the current flow. As I mentioned before, resistance is resistance is present in all conductors. It doesn't matter whether you are a copper wire, whether you use a aluminum wire or some other wire. It doesn't matter it's a stranded, whether it doesn't matter it's a solid core wire. Resistance is always present in all conductors. You can get the resistance to zero no matter what. You can reduce the resistance, but you can't get to the zero. So imagine it's like going a curve like that. So the resistance causes voltage to drop in cable, and the voltage and the resistance are proportional to each other, and increasing the size of the conductor therefore decreases the resistance. So you have a thicker solid core wire or thicker standard wire core that will reduce the resistance. Resistance is measured in ohms, which is denoted by the omega sign here, which I should have put here, sorry about that, or kilo ohms, which is going to be K omega, that is represented that. So sorry, I should have put that in here. So the omega sign look like this, that's ohm, and kilo ohms are denoted by this K, and then we're going to have like that. So those are the symbols that you use. So you should know those symbols. I should have put it there instead of writing omega. But keep in mind that, you know, you will come across these symbols, the omega sign and K omega sign, when you're talking about resistance. Resistance and copper wires. So I mentioned to you that the copper wire is the most common type of wire that we use. And I also mentioned to you that bigger the diameter, the resistance goes down. So if you look at the American wire gauge, when you go down the wire gauge, the diameter of the wire increase because it's opposite to each other, remember from my previous lecture. So the 24 American wire gauge size wire, the wire gauge of 24 will have a diameter of that. And then we know by research that the resistance per every 1,000 feet going to be about 25.67 ohms, and the resistance per 100 meters if you want to, 1,000 meters is going to be 84.2, because meters are, you know, different from feet. So this is just a table that give you that data. You can Google search it. I basically took it from a website right here, the university website, and it basically shows these different type of resistance calculations based on the length of the wire. Notice that we calculate resistance per 1,000 feet or 1,000 feet or 1,000 meters. That because of the length of the wire is directly associated with the resistance. So the longer the wire, the resistance going to be higher. Shorter the wire, resistance going to be lower. So when you are talking about resistance, you need to take into account how long the wire is, not just the gauge of the wire. And also you can see that as the diameter of the wire increases, in other words, the gauge going to go down. What happened here is the resistance also going to be decreased significantly. Look what happened with the 24 gauge wire, which is 25.67 ohms, and it drops to just 0.999 by going into a American gauge 10, which has a diameter much bigger than that of the diameter on the 24 gauge. So in this particular slide, what you need to understand is higher the gauge value, we're going to have higher resistance. Lower the gauge value, we have lower resistance, because lower gauge wires have higher diameter and hence have less resistance over time, over length. And also what you need to understand is longer the wire, higher going to be the R value, resistance, and as opposed to shorter the wire. And when we look at the resistance, you need to make sure that you are comparing apples to apple. So if somebody give you a resistance for a specific wire, you need to make sure that you are comparing that wire to another wire that where the resistance value is calculated with the same length. For if you are looking at 1,000 feet of wire and you're looking at the resistance for that wire and against another wire, it has to be that wire needs to be calculated 1,000 feet of resistance, not 1,000 meters of resistance, because that's going to the calculation going to be different. As the length increases, the resistance also increase. So the key points: bigger the diameter, lower the resistance. In American wire gauge system, that means lower the AWG, the lower the resistance. Longer the length of the wire and higher the resistance. So those are the key things that you need to remember. Inductance. So the inductance can be defined as the transference of electrical energy from one conductor to another. In other words, without actually physically touching the cables against each other, the induction can transfer electrical energy between the wires, as you know, the magnetic field and everything else can take into account. I'm going to introduce magnetic field in the next slide, but just inductance does have a little bit of relationship to magnetic field as well. Faraday law in 1831 stated that the voltage induced in a conductor is proportional to the rate of change of magnetic lines of force that pass through the conductor. So the voltage induced in a current is proportional to the rate of change of magnetic lines of force that pass through a conductor, basically like a B value. This is a very important research, and that's a very important concept that you need to understand. And you know, that's all I'm going to talk about inductance for now for this lecture. Magnetism and electromagnetism. This also has something to do with a little bit of, as I mentioned, inductance as well. So the magnetic flux lines are established between the two poles of a magnet. So if you have a magnet, you're going to have a magnetic flux line like that. So between two poles of magnet. The quantity or density and the length of these lines increases with the characteristic of the medium and the strength of the magnet. So if you have a very strong magnet, there are going to be more magnetic flux lines, and the density going to increase. If you have a weak magnet, what's going to happen is you're going to have less magnetic flux lines between the two poles, North Pole and South Pole, and you're going to have less density of those lines. Electromagnetism is a extension, I would say, of part of the magnetism, overall magnetism. In this situation, what happened, as it says electro, that means include electrical or electronics means of magnetism, where magnetic flux lines are established when the current flows in a conductor. So instead of having a magnet, in this situation, we have a current flow that creating a magnetic field. So the quantity, density, and the length of these lines in electromagnetism increases with the current flow. So if you have a higher current flow, if you have a circuit with a coil like this, and if you increase the I, the current flow increases, the magnetic field significantly increase. So the density and the length of these wires, length of this magnetic flux going to increase in the electromagnetism as the I, so the current flow increases. The direction of the flux lines is determined by the direction of the current. So in this case, the current is flowing this way, so it's flowing clockwise. So the magnetic flux going to be in this direction. But if you reverse it, it's going to go in the other direction. So that's what it meant by that. So this diagram, I put it again from the internet. You can go ahead and check it out. And it just give you a basic overview of magnetism and electromagnetism. Now, why this is important to you? Because these type of magnetism, electromagnetism can impact your noise. So as I mentioned, we're going to discuss noise in this slide, and the noise also has something to do with electromagnetism, because noise mostly to do with how copper cables behave mostly copper cables behave as opposed to fiber optic cables with EMI and RFI that can distort data. EMI is the electromagnetic interference, which has something to do with the previous slide. Remember the magnetism and electromagnetism. So the electromagnetism has a key role with the EMI, electromagnetic interference, and RFI is a radio frequency interference that can also distort data signal. Radio frequency interference can be things like even your microwave oven can interfere with your electronic components and networking equipment. So that would be the RFI. And this can lead to lower bandwidth, poor performance, signal losses, etc., etc. So if you have a situation where there are a lot of noise, that will lead to some issues associated with the performance of your cable. So if you have an Cat5e, Cat6 cable, for example, running near a microwave, every single time somebody uses that microwave oven, it might actually can create a distortion of data. So the noise within an environment in which the cable will be installed should be taken into account. So if you are installing a Cat5e or Cat6 or Ethernet cable, you need to take into account the noise within that environment. If you're putting cables in a microwave tower, for example, you may want to put some EMI, RFI shielding in your Cat6, Cat5 cables, because those microwave towers produce a lot of microwave energy that may distort your signal. So basically, imagine you have a signal. So you have a nice signal right here that is carrying data. So this could be a digital signal, this could be analog signal. So in this situation, I'm just showing you a digital signal here. I pick it up from the internet again. And then the noise could be some bunch of microwave signals. And what happened when the interference happened, this clean signal get mixed with this noise signal, and it's going to produce a signal pulse with noise. So you still can actually most of the time can trace that your original signal, but that original signal going to have all of these unwanted noise. This is not good. It can lead to lower bandwidth, poor performance, and also signal losses. So we need to think about mitigating those things based on where you install the cable. Again, you can purchase cables with those shielding already built into your cable. The cost gonna go up with those type of cables as opposed to regular cables that you might put, but that will prevent noise from being an issue on your cable installation. So you need to think about noise in that regard. Type of noise includes the short noise, flicker noise, thermal noise, transit time noise, atmospheric noise, crosstalk. Crosstalk happen when you put a whole bunch of cables together, bundle up in a one single bundle. That could create crosstalk where interference, EMI and other interferences create crosstalk between two cables. Man-made noise or industrial noise, impulsive noise, low frequency noise, intermittent noise, and continuous noise. I'm just introducing you to types of noise here. I will go into depth in a very separate lecture, which I will go into depth of these noises, because currently this lecture is over 30 minutes long, so I don't want to take up more time. So I'm just gonna introduce you to these noises that exist, but I will talk about these noises in depth, in technical details, in a different lecture. So I'm going to briefly introduce you fiber optic cabling associated fundamental concepts, but I will again not go into depth of these things in this lecture. So fiber optics use photons, in other words light pulses, as opposed to electrons which use electricity. So all the Cat5 and Cat6 cables are doing is sending electrons, as opposed to fiber optic cables, we are actually sending photons or light. Yes, we are doing packet switching in both of these situations, but one is using photons or light, the other one is using electrons or electricity for communication medium. And fiber optic cabling can represent digital signals at ease, but you can also use analog signaling in fiber optics as well. No electromagnetic interference or radio frequency interferences that you should be worried about, because we are using glass fibers as opposed to metal cables. But interference can sometimes do happen. But 99% of the time, you will not come across any EMI, RFI issues with fiber optic cables. What you should consider is the use case scenario, like where you are installing, as I mentioned, the bend radius and termination, etc., which I previously have mentioned in this lecture. How would light represent communication signals is something very important that you understand. But however, in this lecture, in this particular video, I'm not going to go over that, but I promise I will post a separate lecture on my YouTube channel describing how light represent communication signals. When it's come to the point fiber optic signaling, this is a basic overview, typically used in digital transmission, but analog signal can also be transmitted through fiber optic cables, as I mentioned before. And what you need to understand is we are using light here as opposed to electrons. We are using photons instead of electrons, right? And the fiber type is something that you should take into account, because there are single mode fiber, graded index fiber, and step index fiber. Single mode fiber can support a bandwidth up to 100 gigahertz per kilometer, and the graded index can support either two types. There is 500 megahertz at 1300 nanometer wavelength, as well as 160 megahertz per kilometer, that is 850 nanometer wavelength. And then we have the step index that allow 20 megahertz per kilometer. So what you need to understand here is that, you know, there are types of cables that you need to take into account when you are installing fiber optic signaling type of fiber optic cables. And there are, you know, single mode, graded mode, and step index, and they have different bandwidth parameters. Again, I will go into much more technical details and depth in my future lectures on structured cabling. For now, just remember these do exist and keep that in your back of your mind. And that would bring us to the end of this lecture. If you have questions or concerns regarding any of the topics that we have covered, please feel free to reach out to me. If you like these type of lectures, please thumbs up this video and subscribe to my channel. Until next time, thank you so much and have a nice day.